So where do you want to start specifically? Do you have any
Um,
like specific questions?
no specific questions. I definitely just want to paint a bigger picture, I think.
Okay, all right.
But yeah.
Okay, cool. Sounds good. So I think personally, I think the best place to start then is just right there, sort of with the carboxylic acid chemistry. Uh, a little bit before it, basically, I don't want to, I know you know, but the general idea of carboxylic acid chemistry is that you're going to have those, that you're going to have both like a nucleophile and an electrophile in one molecule, right? So where's going to be like the most nucleophilic versus the most electrophilic part or parts of that molecule of carboxylic acids and all that other stuff.
Um, the most let's see if I don't mix up my terminology. The double bonded O will be more electrophilic, but the OH will be more nucleophilic.
Double bonded O will be more electrophilic, and and what will be more nucleophilic?
The alcohol and
Okay. Oh, I see what you're saying. Okay. So mostly, yeah. So that means that you pretty much know exactly what I was asking, and you were taking it another step, making it harder. So basically, like the carboxylic acid, and it's kind of the same with, well, it is the same with all of these carbonyls. It's just that you've got this C double bonded to an O, generally speaking, and whether we have an aldehyde or a ketone really doesn't matter that much. The main difference between the aldehyde and the ketone is, well, obviously this H versus that being an R. And it's simply that you can't oxidize aldehydes as hard because they will turn into what? So like if I take, like, for instance, I think it's KMnO4, something like that, or like you could also say the CR2O7.
mm-hmm.
If I do either one of these reactions, this would be two different things, obviously. Uh, what's my product going to be if I have this as an aldehyde?
You're gonna have the
And I could just pick one of those, like I just
yeah,
get rid of that. But
sure.
it's they do the exact same thing.
If I remember correctly, you're gonna have a because you don't want the you don't want the OH, so it's literally just gonna turn into the CR and then H2O.
Okay,
Or no.
so the
C and then like
CR.
the R group and O will
Oh, I see. I
no.
see what you're
O will not leave.
saying.
It will turn into OH.
Yeah. So, okay, the O, which O is gonna turn into OH?
So yeah. So the double bond's
But
gonna
I guess,
break. It's gonna be a single bond with
okay,
the O needing more electrons. Um, so
okay,
the hydrogen will bond there.
yeah, yeah, okay. So yeah, and so what you're gonna end up with on this, I'm not sure exactly what you're saying. It's you don't have a pen or anything that you can write on a screen with, do you? I think I've
No,
asked you this
unfortunately
before.
not.
Okay, no, it's fine. No, I don't think I've ever had anybody actually take me up on this offer, but I always offer people, because I think if you had a pen display, I have it set up to where you can write on this also. But with this reaction, basically what you're going to end up with is just the carboxylic acid form of this thing. And it's just because you
Oh, right.
over
Yes, yes,
oxidize
yes.
it. And my question was actually kind of bad here, because what I meant to write was not starting out with the aldehyde. I meant to start out with the primary alcohol. So just like an
Oh, right.
ROH here. And so if I take like one of these really strong oxidizing agents, like the CR2O7 thing, and try to oxidize a primary alcohol with it, we're actually
Mhm.
going to skip over the aldehyde. We're not going to be able to form an aldehyde with a really strong oxidizing agent here. We're actually just going to skip over it and go ahead and oxidize it again and form a carboxylic acid. Whereas with the ketone version of the same thing, you know, like if I were to have, or not the ketone, I keep wanting to skip the alcohol. So versus if I had like the, for instance, we'll just say like some secondary alcohol, right? Like this, I don't know. If I have some secondary alcohol and I use that exact same thing, then I'm going to end up at a ketone before or without going all the way to the carboxylic acid. Why is that? Why do you think that is?
Um, because a secondary alcohol has more steric hindrance, and so it won't or it won't oxidize as much initially unless you have like a second step there, just because um it won't be able to properly reach the alpha carbon.
So it's actually not because of steric hindrance. It's simpler than that. It's simply
Oh.
because in order to get to the carboxylic acid
Hmm.
from this ketone, I would have to break a carbon-carbon bond.
Oh, right,
Versus
right, right.
up here on the primary alcohol, I don't have to because, you know, like my intermediate obviously is going to
That'll
be
be a
that
carbon
aldehyde that I,
oxygen bond.
yeah, or just this carbon hydrogen bond is the only thing that has to get
Gotcha.
broken here in order to get to, and that's just not as big of a deal. Like we can displace hydrogen because if you think about it, hydrogen, the hydrogen ion is a leaving group on its own, and so you can displace a lot more easily than you can break a carbon-carbon bond. This is so
Right.
crazy. Monitors keep rearranging themselves. Just unplugging that. Oh, please come back. Okay. I just unplugged one of the monitors to make it stop like going black on me. So that's the main thing to think about here. And the reason why I'm starting out with these is because this is the kind of thing, this is what I was hearing whenever you're telling me that like you get really caught up in details on some stuff. And like this seems like a thing that would annoy you because this is the kind of thing that used to drive me nuts because they talk about, I felt like in OChem, we talked for a whole semester about how important it was to push electrons around. And then we just stopped doing it. All of a sudden, it started just being like, no, memorize all of these. These are oxidizing agents. What do oxidizing agents do?
Yeah,
But
I was way more focused on the memorization than like why it was happening.
yeah, I wanted to
Um,
know why it
yeah.
happened. It just seemed like there was nobody that wanted to say why. But
Yeah.
I don't know that. But so thinking about these, what I would do if I were you, and I can just send you these notes that I just made, if you want. I think I typed all of this stuff. Um, I think the best approach for these is just to memorize. See right here, I just put oxidizing agents, and this is pretty much like all of the strong oxidizing agents you're going to see on the MCAT. And so if you just memorize these things and know, I didn't put this one's abbreviation. This is the PCC thing. And just know that whenever you see them, that means that something's going to get oxidized. And in terms of OChem, generally that just means more bonds to oxygen. And
Mhm.
so like that will get you a long way because you'll find that, and this will make a lot more sense once we start doing practice problems, but you'll find that the OChem on the MCAT isn't that bad because you're always, oh, sorry, I didn't mean to make it go away. If you were like, but I mean, this is way, no, I can't find it again. The the OChem on the MCAT is going to be just very, it's going to look like the OChem passages look the most intimidating of all the passages by far. But
Yeah.
if you just approach them with some degree of confidence and just rely on the basic fundamental principles of like nucleophilicity, electrophilicity, steric hindrance, that sort of thing, then you'll find that you just end up with all the answers because you don't have to draw this stuff out. Like they're not going to grade your Lewis structures. You don't have to generate your own answers. Basically, it's all multiple choice. So it's going to be a process of elimination more than anything. And that'll make a lot more sense once we get to the actual practice questions. So so the one exception with these strong oxidizing agents and this reaction where we send the primary alcohol straight to the carboxylic acid is PCC. And that's the one that will actually be able to reduce to to oxidize to the aldehyde. The rest of them will just make it go all the way to the carboxylic acid. So just FYI more than anything on that.
Yeah.
All right. And so, sorry, I kind of went off on a tangent on that a little bit, but that's something that I think that is, and mostly what I'm doing here is just emphasizing that I don't personally even know the, like electron pushing mechanisms to get to, the carboxylic acid from this primary alcohol. I just know that these are, the chromium stuff and the manganese and all that garbage is classified as strong oxidizing agents. And so just as a general rule, this is one of those things that you kind of just are going to have to memorize, that the strong oxidizing agents will take the primary alcohols to the carboxylic acid, whereas the secondary alcohols will just go to the ketone because you would otherwise have to break a carbon-carbon double bond. So they're both going to get as oxidized as they can without breaking a carbon bond, basically.
Cool. Okay.
All right. And so does it make sense that the carboxylic acid is more oxidized than an aldehyde or a ketone, for instance?
Yes.
Yes. Are you sure? I sounded like a question.
No, I just thought you were gonna ask me why, and then I knew I couldn't answer why. I just know that yes, it is more oxidized.
Well, I'll bet you can answer why. I mean, or can you answer why, why you can know that? So for the carboxylic acid, you've got this, right? So the only difference between the aldehyde and the ketone versus the carboxylic acid, is just that, well, here's the ketone and here's the aldehyde. So it makes sense that the thing that has the only difference being the stuff in yellow, it makes sense that the one that has oxygen in yellow, right? Yeah, versus that aliphatic stuff is going to be more oxidized. It's just got 3 bonds to oxygen. What's the only thing that's more oxidized than a carboxylic acid? And I'm saying carbon based.
Are the esters more oxidized?
No.
No, because they have the same. I would say they can have the same amount of oxidized. Yeah.
Right. Yeah. So I would say that they're the same. You could be a smartass or some. The one answer that I don't want you to give me is just because you'd be right, but it'd be missing the point, is something like this, right? If that's fluorine here, because technically that's more oxidized. But what I'm actually asking
anything
about,
with the halides would be more oxidized.
No, just fluorine, because
just fluorine. Okay.
Yeah, because if you think about it, and I mean, this is something they would never ask you about, because fluorine is just the only thing more electronegative than oxygen. And so it's basically how much really electronegative stuff can we form bonds to? And so I would say that that's very much splitting hairs, and I would put those two on, the same level. Because they're things that effectively have 3 bonds to really electronegative atoms from carbon. And so the only way to get more oxidized than a carboxylic acid or than, the acetyl halide is to have just CO2. That's the most oxidized that carbon could possibly be, right? And so,
yeah.
And so
you're all of its bonds go to the oxygens.
Yeah, exactly.
Okay, cool.
Yeah, and something that is one of these big, massive overarching trends that we're going to talk about is you're going to find that the more bonds a carbon has to oxygen, the generally less useful it is to us as heterotrophs, or generally, animals that eat other animals, the less useful it is to us energetically, because we turn carbon hydrogen and carbon carbon bonds into carbon oxygen bonds and get energy out of doing that. And so the more bonds, the more oxygen there is per carbon in a molecule, the less energy there is there for us. That's why we store energy as, fatty acids, because they've just got lots and lots and lots of this, right? Very little oxygen in the carbons, versus, like glucose and stuff has a lot more oxygen present. So that's just something to be aware of. And then obviously like this, the waste products. So everything that we're going to talk about for the next couple of weeks is going to be primarily like, how do we turn carbon and carbon hydrogen bonds into carbon oxygen bonds, and why do we get energy from that? And so like all the various different strategies of doing that. Okay, so continuing with the carboxylic acid business, and now we're going to get to like some of the actual chemistry behind it rather than just considering these molecules. But considering the molecules really is probably more high yield than all of the reactions. Like if you could split OChem in half, stuff that's not reactions and stuff that is reactions, it's probably the former that would have way more points involved, like intermolecular interactions and stuff like that. So this is what I'm going to refer to as a general like carboxylic acid backbone. Okay, so that's like your general carboxylic acid. There are a number of other molecules that share that same format, same setup, that aren't actually themselves carboxylic acids. One of them would be like you mentioned esters a little bit ago. So an ester would be just like one example of another carboxylic acid backbone molecule. And, because it just has same thing, right? But then we have an R there instead. So what are some of the other ones?
Amides.
Okay, perfect. Yeah. So they've just got this, and then what?
Nitrogen.
Yeah, nitrogen. And then you can have
with like R groups or yeah.
Right. Yeah, I'm just gonna put 2 R's here, but you have 3, or you can have H's and R's and some mix of them, right? Okay, cool. So my R's can be H also. What are some other ones?
Like the big version of esters. What are they?
Okay.
Just the bigger version of ester. The anhydrides.
Yeah, for sure. Nice. Okay, anhydrides, which are the big version of esters, right? So you've got 1 R, this thing. So if you had an ester, you could get this far, right? But then it turns into, I'll just go ahead and write this. I'm gonna try to go fast through some of this rather than like making you. So I think what's another one?
With phosphate. What is it called?
Huh?
When a phosphate group is attached.
So that would just be like a phosphate ester, or like a phosphoester. Yeah, so that's not one of them. But it could be one of them. It is technically, but it would just fall under the ester category. But you're right otherwise. So
are fatty acids not? Never mind. I don't.
They're esters.
They're esters. Yeah, I'm pretty sure they're part of this.
Technically, when they're acids, they're carboxylic acids. But when you're in, but when it's in like the triacylglycerol form, then they're esters. We can talk about that reaction specifically, and that's actually where we're going. We'll go there in just a second. You've got like one more of these to identify, though. I think
one more.
I think there's one more.
I can't think of it.
Okay, so and it may not be perfectly clear just because it is a little bit different, but you already mentioned it once, so I know you know what they are. It's just the acyl halides. So like X there, where X could be F, Cl, Br. Not so much F though, because the way that we think about these now that we have all 5, with counting the carboxylic acid as one. One thing that's really important to recognize is the various reactivities of these things, but not just to have it memorized, but to like actually understand why they are, why they do have differing reactivities. So which of these is the most reactive?
Um, Discluding F,
Do what? I'm sorry.
discluding F or fluoride,
Oh, I just
fluorine.
mean like of these five. Yeah, and yeah, we got rid of fluorine.
Sorry,
You're saying
sorry.
forget that. Yeah, so like
Um,
1, 3, 4, 5. I'm
sure.
not saying
I
not that
think,
order, but
yeah, I would say the halides would be most reactive
yeah, yeah,
because
for
they
sure.
want to leave, or the the yeah, they want to leave.
Perfect. Yeah, exactly.
Um,
And one really good way to think about it, and you may already be there because of what you said, but I just wanted to focus on it because you did kind of make me think about it, is if you think about how good the various different leaving groups are whenever these things are reacting, then that gives you a really good clue on how reactive they are. Like if it's a really good leaving group, then the thing's probably going to be quite reactive. And you can consider like, okay, well, if I didn't have this whole like R carbon, O, this, like if I didn't have this whole bit attached to the question mark, if it was just a proton, so if I had just
mhm.
question mark proton, how strong of an acid would this be? Depending on,
Oh,
like
okay.
question mark proton. And if it was, well, one of the halides, HBr, HCl, HI, then super duper strong acid, right? But
Right,
anything else, like all carboxylic acids are just going to be weak acids. And so
right.
that's a really easy way to think about that, or at least to get the first answer. But so what's the next most reactive then?
Um, Nitrogen or amides with
So
nitrogen groups.
those are actually going to be the least reactive of all of these.
Oh, true. They never want to. Yes. Okay. Okay. Um, it would then be uh, in my mind, anhydrides like don't really want to split because like you have to. But I guess I think I'm overthinking it.
I think you are too. So
Okay, so anhydrides would be next, and then
yeah,
esters.
yeah, because and so correct me if I'm wrong, but I'm guessing part of what you were thinking about with the anhydride is that if you're gonna break this thing up, that one of these things is going to have to just be like a carbon off by itself. Like the oxygen can only go to one side. So then
Right.
this looks like it'd be something that's like relatively like unstable. But in reality, if you're going to react it with something, you're always going to have, some, we could say like some nucleophile, just say nucleophile with its negative charge coming in and attacking one side or the other. Right. And so if I attack, for instance, this side over here, with, just on the right side, just arbitrarily picking one, then that
Hmm.
means that these electrons go to here. And so we've got the thing that would be relatively stable. It
Hmm.
goes off on its own, right? The quote unquote leaving group. But then you've got the nucleophile attached to the other side. And so it's neither side is going to just be like a carbon floating by itself because you're going, like when it breaks, it's going to break into these two things.
Okay, that makes sense. Yeah, yeah.
So whichever side is the leaving group is itself just like a carboxylate anion.
True. Okay, so in that same vein, then it would be esters and then carboxylic acids.
Which one is more reactive between those two?
Esters would be more reactive?
Um, I
No.
have to think for 1 second. I can't, I don't know why I can't think. Yeah, what do you think? I know now.
Um,
They're gonna be really similar, honestly. Like I don't want to make it seem like that's like $1 million question or anything, but
yeah, I feel like no, I stand by my answers. I think esters are still more reactive.
you say esters are more.
Mm-hmm.
I think in reality, and we could look this up because it's probably going to vary a lot depending on what your reagent is and all of that. But I think that
Mm-hmm.
the carboxylic acids are going to be slightly more reactive
Okay.
than the esters are. And reason being, I'm using the because I think I'm looking at I Googled charts just to check myself on this a little bit ago, and I've seen them both ways the whole time. So
Okay.
but some of these charts are garbage too. Like some of them have the acetyl halides as the least reactive. So whatever. But I'm just looking at Google Images. My thinking on because this actually does matter to some degree. The reason why I'm thinking that the ester might be somewhat somewhat less reactive than the carboxylic acid is because your leaving group is either going to be, well, in the case of the ester, your leaving group is going to be RO with this negative charge on the O, versus in the carboxylic acid case, it's going to be that, right? Just O with, and it's whether you have an H or an R. And so then you have to think, all right, which of these two things, just like what I was saying above, where you consider the acid and it's this being a conjugate base. So if you had like CH3OH versus H2O, which of those is a stronger acid? And the one that's a stronger acid is going to be the one, well, that means that, like if H2O were the stronger acid, then OH would be more stable in solution by itself than CH3O minus.
Yeah.
And in reality, again, those are going to be very, very similar. That's why I'm kind of torn on it. But the CH3O minus is going to be a little bit less stable in solution by itself because carbon chains are electron donating. And so we want, in order to stabilize that negative charge, you would actually want something that's electron withdrawing. And the hydrogen is just going to be, the hydrogen doesn't care. It's going to be agnostic to the negative charge. Whereas like the longer I make this carbon chain, the more electron donating it's going to be, which just increases the problem in terms of, like having negative charge on that oxygen.
Right.
So that's why I'm saying maybe a little bit more. But in terms of ester versus carboxylic acid, doesn't matter that much, but I could definitely see them making that a right answer to a question, like where you do have to make that decision just because they're assholes whenever they write this test. And I mean, they just, they're trying to make the test as hard as they can. And that's, so that electron donating versus electron withdrawing thing is a concept that they probably don't, I know they mentioned it briefly in the book, but probably not mentioned nearly enough, just in terms of like how frequently you end up using it. Just paying attention to like what groups are electron donating versus electron withdrawing. So briefly, I want to focus on we already talked about why the acetyl halide is the most reactive and hydride usually going to be second most. I want to talk for a second about why the amide is the least reactive though. So one big reason that you could think about just right off the bat is this, whenever this is an N, and it could be like, well, I'm just going to make it NH2 for now. So whenever this is an H2, for this thing to ultimately like end up leaving in a nucleophilic attack, it's going to have to take these electrons with it. And so what's going to be more stable with just carrying around a negative charge? Nitrogen with negative charge on it or oxygen with negative charge on it?
Oxygen would be more stable.
Right, because it's a little bit more electronegative. And so for that reason, you could presume that the amide is less reactive, but it's actually even crazier than that. It's or crazier. That's not super crazy. It's not gonna like keep me up at night, but it's actually got a lot. It's even more stable than you would predict based just on that. And it has everything to do with this partial, it's kind of hard to say, but all right. So what would be some resonance structures for this molecule of this amide? Obviously the primary one is the one we've been drawing, right? This thing. I'm going to make the H's stick out now. And I'm drawing a lone pair of electrons here. Okay.
Beautiful.
So thanks. All right. So what would be another resonance structure for this molecule?
So rather than the double bond being towards the oxygen, it would be with the nitrogen molecule, and the oxygen would hold a negative charge.
Okay. Yeah. So these electrons would jump up here, right? And then this lone pair has to jump down here between the nitrogen and the carbon. And yeah, so you end up with this thing where you've got that negative charge, and now you have this double bond, nitrogen. All right. So what are some things that change here? What's something that's really, really important that is now totally different? Think about the geometry around the various different atoms.
I think rather than the nitrogen being in like a more tetrahedral formation, it's now like forced to be, I don't even like, not trigonal planar, or yeah, trigonal
Yeah,
planar.
yeah,
Yeah.
trigonal planar. Yeah, because it's sp2 hybridized now, so it's only got
Mm-hmm.
it's only got electrons in 3 directions basically. And so yeah, so it would want to, quote unquote, want, insofar as these things want things, to have these be about 120-degree bond angles, because you've only got electrons in 3 places, right?
Right.
So if this is trigonal planar, what's the geometry on the carbon that's next to it?
Oh God. The geometry on the carbon. Is it also SP3 or
Or
SP2?
it's at sp2. Yeah, and it was before as well. So it's also got 120-degree bond angles, whatever, right? And so if both of these are trigonal planar, both are trigonal planar, that means that in order for something to be trigonal planar, that means that it and all of its substituents exist in a singular plane. Like, you don't have to go into a third dimension. And so what that tells us is that this carbon and all of its substituents, nitrogen, oxygen, R group, are all in one plane. And this nitrogen and all of its stuff is all in one plane, right? So this is all literally, the whole thing is
Mm-hmm.
in one, is a flat molecule. It all
Okay.
exists in one plane. Whereas, and so that's going to have, I've seen this on several questions in the past, but that's going to have a lot of relevance to the rest of whatever, maybe if it's in some sort of a ring or something, that's going to mess up the ring quite a bit. But in terms of just why this is the least reactive of the carboxylic acids, if you think about this is like not an insignificant resonance structure. And so this double bond character here means that the carbon nitrogen bond in the amide is a lot stronger than just the single bonds carbon has to all the other stuff and all the other carboxylic acid backbones.
Mm-hmm.
So the reason it's way less reactive is due to this, what we would call double bond character. So it's not a double bond, but it's also not a single bond. It's like a 1.5 bond or a 1.3 bond or something. I don't know.
Okay.
And so that just makes it, if you look up like the enthalpy of the bond formation or whatever on the amides, it's much greater than the rest of these. So it's by far the least reactive of all of them.
Okay.
Yeah.
That makes sense.
So, okay, cool. And so there is I don't want to butcher it right now. And I don't want to waste a bunch of time on this, but there's a molecule, I'm trying to think okay. So basically like this molecule where you've got this ring here. I think it exists like that kind of. Yeah, it's something like this. Yeah, I don't want to mess this up too much. But anyway, so this molecule has like an amide that I'm gonna find the actual picture later. I'm gonna show this to you later because I'm
Okay.
just gonna screw it up. It's basically like why penicillin does its job, is because
Oh.
of this amide forcing everything into a plane. But if we had a whole bunch of time for me to stumble through it and try to draw a terrible picture, I would. I know I have it in a folder on my computer, but I'm not about to start clicking around on this computer right now. I know that it's going to crash as soon as I do. Okay. So yeah, that's some of the info about the amide. All right. So let me think. All right. Covered all of that. Just trying to, so do you know what the reaction mechanism would be for, just generally speaking, like a nucleophilic substitution on one of these carboxylic acid backbone molecules? It's like
Yes.
a terrible way for me to ask that, but I'm just trying to be like economical with time.
Or like, does it depend? I
Essentially.
think so. Yeah.
Right. Okay. All right. So Okay, so yeah, I don't know. I'm torn because a lot of what I would do now is go through those a few examples of those just because they are really important mechanisms and they're pretty simple though. I don't know. Here, I just want to make sure.
When discussing like
This-
E2, E1 versus like SN1, SN2.
So I'm just talking about like a transesterification reaction, basically. So
Oh,
like,
sure.
so we've got, for instance, this ester that's O, we'll say OMe. So that's a methyl group, right? This Me.
Mm-hmm.
People get confused by that. Like I wasted like an hour in a Kaplan course one day because nobody in the course knew what the Me meant methyl, and they were all just totally lost. I went through this for like an hour and nobody spoke up until the end of it, and one of them raised their hand and was like, what does Me mean? And so it's been like literally an hour. So I just make sure that people understand that now before I go into this. All right, so we've
Yes,
got that. Put it in. So we've got Na positive, O negative, Et here. And we put this in ethanol. Okay, so what's going to happen? Walk me through it.
First, it would, okay, wait, I need to draw this out for myself real quick. It would take, oh no, it already has a methyl. So it would make a, oh my God, I wish I could draw on this. Okay.
Yeah, I know. I'm
It would
sorry.
make a carboxylic acid and then another one that was methyl, the methyl group, the O, and the ethyl group.
So it would make a carboxyl, like OH. Carboxylic. Okay, so what's the first thing that would happen in the mechanism? Like
This
just
would
from this
react.
step right here.
Sure. The negative charge on the O would want to hit the, I say hit, hit the alpha carbon so that the,
So the alpha carbon, just FYI, the alpha carbon would be this one. Right.
oh, right, because it's next to it. Okay, so the
Yeah.
first carbon, the one that like has the double bond with the O.
The
Not the
carbonyl.
alpha
So it's
carbon.
just going to be the carbonyl carbon. Yeah.
Yes,
No,
the carbonyl carbon.
everybody makes that. Everybody makes that mistake. I knew you knew. That's why I just said it. I just wanted to make sure though, because
Yes.
literally everybody makes that mistake. Yeah. So it does that, and then
So
what
that
has
double
to happen?
bond would give the electrons to the O, so that would be O
Okay.
negative.
All right. So now we've got this, and you would call this a tetrahedral intermediate because now the thing went from being sp2 to sp3. Okay. So now what?
Makes sense. Okay. No, sorry, drawing it for myself. Okay. So now there's a lot happening. We want to from this tetrahedral intermediate, the electrons would go back to form a double bond because that is the more favorable or more stable for the molecule. Right. Which means that the carbon now would have too many bonds, so it has to break its bond with the O methyl group.
Okay.
So that would be the better leaving group.
Okay.
Yes. And as it breaks off, the hydrogen would also react, correct?
Which hydrogen?
From the ETOH.
Why? Sorry.
Well, because
Oh,
you
you
don't
mean
want
like
it
it
to
would
just,
donate its hydrogen to
it would
the
donate, yeah, it
OME?
would donate the hydrogen, because
Well,
you don't just want like an O neg with a negative charge like floating around.
but then you would just have one on the ETOH, right? Because you're talking about the difference
Oh,
between these two
sure, yeah,
molecules, right? But
yeah.
and so you're right, kind about half the time, because those are about equivalent when it comes to pKa and stuff. In reality, like the OME, for the same reason I was talking about earlier with the water versus the alcohol being deprotonated, the OME is going to be a little bit more acidic than the OET, just because ET has a ethyl group attached. So it's a little bit more electron donating than the methyl group that's attached to the OME. See what I'm saying? But again, it's like almost identical, almost the exact same thing. But yeah, you're 100%. So I almost said you're 100% right. You're 50% right, because it would happen about half the time. Yeah, and so you end up with this product. But how do you know that you end up with this product? Because for the same reason that those two are about equally acidic, they're also about equally good leaving groups. They're about the same, right? Because in one case we have an OME leaving, in the red that I just drew, but you could also have the OET leave, and then you would just end up with the same thing you started with, right?
Sure.
Like you have the OET left. Yeah. So why don't you? Because this is going to overwhelmingly form this. It's not going to be like a 50-50 thing.
Yeah. I thought it was because with the ethyl group it would be more stable, but now I'm uncertain.
They're going to be almost identical in
Yeah, because
all
they're both
things
just carbon
stability-wise.
groups.
Right. So it's kind of a trick question. I don't want you to have to like think about it too long, but it's not like just a fun trick question. It's they do this like crazy. So the reason that we're going to overwhelmingly end up with this product, the one that I circled in green, is because of specifically the solvent. Because you're going to continuously get to this spot, right? This tetrahedral intermediate spot. You're going to arrive at the spot over and over and over again, because you're always going to have one of those two species in solution deprotonated, right? But if you think about, let's just say we've got 1 mole of stuff, right? But then we've got it in the solvent. And as long as it's not like super duper crazy concentrated solution that would just be impossible, you're going to have way more ethanol than methanol in the solution. Like way more, because it's the solvent. See what I'm saying? And so like every time we get to the tetrahedral intermediate, every time that we go backward to our reactant, we're just going to form it again. And like 10 to the 23rd to 1 times, you're going to end up with this ester being formed, just because the thing on it that is attached is the solvent. And so that's why.
This is actually a really good spot to end, because now I gotta run.
Right. Yeah, no, I was watching the clock.
Yeah,
sorry, we went over 1 minute.
Okay, thank you so much.
Yeah,
I'm
no
gonna
problem.
blast. But can you actually, because I can't stay any longer, but can you text me what to have ready for Friday?
Yeah, absolutely. Go ahead and get out of here, and I will talk to you. Yeah, no problem. I will talk to you later. So sorry for all the technical difficulties.
You're good. Thank you. Bye.
Yeah, no problem. See ya.